Thank you very much. We think we can go for the second question, the second talk, please. Sorry. So that will be given by Jason Morgan from Princeton, and the title of the talk is My Perspective on the Origin of Plate Tectonics and How Space Geodesy is Changing It Today.
This was sort of how mountains were made with the ideas of continental drift, is that these continents moving through the mantle, the leading edge would be crumpled up in mountains, you know, like the Andes or the Rockies, and you had a direction each one went, and the trailing end was more flat. Whoops, okay. Now, Holmes started with the idea not of forces near the surface driving continents apart, like Wegener and all had. He had convection in the mantle, pushing them around. But he kept a lot of the ideas of continental drift. You can see the leading edge crumples, the trailing edge is more passive, and he left behind pieces of continent that were the mid-ocean ridge or Iceland, and whoops, here we go. But then, starting in the 50s, there was just a revolution of data, and as you can see in the United States in the 20s and 30s, there were only, as far as I know, only 3 ocean-going research vessels. England had them, and Germany, and other places did too. One of them was by the Carnegie Institute of Washington, the Department of Terrestrial Magnetism. And this ship was especially to map the magnetic direction of the whole Earth. And a wooden ship is very good for that. But as you see on the bottom, there are disadvantages with wooden ships. It didn't last. It only had like I think it made six voyages around the world and burned. But at the end of World War II, there was certainly a lot of ships available. This is a seaplane tender that was essentially a hangar that would pull into a lagoon or something and refurbish seaplanes. You had to rebuild the engines every 2 weeks or so. They had to have an overhaul, and every month you had to really change all the piston rings. And these little ships, this one was the one that became the pioneer at the end of the war, but there was just an enormous burst of new activity, new techniques invented, and it was sort of a revolution of seafloor knowledge. Hess was very involved in this. He had been the captain of a ship during World War II, and his crossings from the west coast of the U.S. I think there were like 4 or 5 voyages to the Philippines and to and unlike other people, he kept his depth recorder running the whole time. He said, "Oh, there's no Japanese here. We'll just forget about that rule of turning it off," and became very interested in the Pacific floor. He summarized these results in he proposed instead that there was the upper layer of the Earth was cool, was very strong, very solid. He or Elsasser at the same time called this the tectosphere. Its name has changed to be called the lithosphere nowadays, which was an earlier word. And that the ocean floor, the continents, they all drifted together. They were a solid piece. There was convection going on. And I have heard several people at Princeton who were there when this was discovered say that the spark of this came in about 59, and it was from heat flow measurements that Maxwell and von Hertzen had shown that right at the crest of the Pacific rise, there was a spike in the temperature measurements that were being made. It's similar to what Xavier just said, that the idea of the high temperature right at the crest was just the trigger that gave him this idea that he called seafloor spreading. And he wrote this remarkable paper, and it's remarkable for two reasons. One is there's absolutely no data in the paper. He just summarizes the general knowledge. There were a couple of cartoons, but at the end of this paper, he says, now, if this is all right, this is what it predicts. And he went through 19 separate consequences of this idea of seafloor spreading. And two of them were wrong. And he thought that the ocean crust was serpentine, that it was as it rose and it got below the temperature where serpentine existed, there was an interaction. And basically the seafloor was covered with sediments. There were no drills, and where you had samples was in fracture zones. And you can find ultramafic rocks and serpentines in fracture zones. It's just not, he thought this was the entire oceanic crust. But I really recommend that you look at his original paper, and it's quite an amazing leap of faith. And I don't know what happened. Now, at this same time, the magnetic anomalies in the Pacific were discovered, that the Pioneer was one of these ships that was converted to be a research ship, operated in the Pacific. And there was a map made of the West Coast for, the real purpose was that the Navy wanted a detailed topographic map for submarine practice and such. And that data is classified. That was not released. But Rafe and Mason towed a magnetometer behind the ship that had been invented to detect submarines from blimps, that you would fly along and you'd see a magnetic anomaly. You could sort of find a German submarine that way. And they towed one of these developed instruments behind. And well, the Navy said, well, we don't care about the magnetics, so you can publish that. You just can't publish the bathymetry. And they had this remarkable discovery of these long linear magnetic anomalies that were a complete mystery. And for several years, there was wide-ranging debate as to what had caused this. It was thought it was variations in the susceptibility of the magnetic floor, or maybe height. And from this data, Vic Paquier noticed that if you looked at the little pattern of anomalies here and the pattern of anomalies at B that are 1,000 kilometers away, it was the same signature, and that this was a great fault that they, as they called it, with more than 1,000-kilometer displacement on it. And this was a big mystery. Fred Vine was on a British ship in the early 60s in the Indian Ocean, and they were mapping crossing the Carlsberg Ridge between Africa and India, and there were a lot of seamounts, and they discovered these things, but some of the seamounts were normally magnetized and some were reversed. And he came up with this idea that you just, he could combine the idea of seafloor spreading that had just coming out with the idea that the Earth's magnetic field underwent these periodic reversals. And you could put these two hypotheses together and explain the parallel stripes in the ocean. Okay, now at the same time from the ridges, Hess had been involved very early, since the 30s, with the idea of using the gravity anomalies that had been discovered mostly around Indonesia, that and other ideas that people had of these tectogenes and down buckles, and that this was a mechanism that was occurring and perhaps was making mountains. This is a lab experiment of having layers of different densities and squeezing them and making these down buckles that Hess had called tectogenes. And this is a real neat thing that Griggs couldn't do convection to drive this, but he had little rollers, and if you cranked the little rollers, it would force the motion that would be similar to something going down. And this is sort of where, at the time that I first switched from a physicist to becoming a geophysicist, I was working on relativity and gravity and such with Bob Dickey, and was really frustrated that the theory was very far ahead of any data. And I was studying the rotation of the Earth and trying to, with the idea that if gravity and the Earth changed, the Earth would shrink, it would spin faster. But more importantly, if gravity was stronger, the orbits of the Moon and Saturn and Jupiter and things would change, and comparing the two to see if you could find any evidence of a gravity wave with periods of months or years or something. And I learned there was so much data available in geophysics that I became more interested in that physics was theory-rich and data-starved, and here the Earth was just filled with data and without explanations for some of these things. But when I switched into marine studies, my textbook where I learned things was basically this book by Bill Menard. This was where I really got into it. I read Jeffries and the other textbooks as well, and there is an equivalent book for the Atlantic, came out at that same time. It's these 5 papers by Xavier, and this is essentially the equivalent for the Atlantic. I think there are just as many words in these papers as there were in that book. And this became your thesis in Strasbourg? Is that? Yeah, was this. So I was working on trying to understand trenches, and had this paper in 65. It essentially was that if you had a mass that was sinking, it created a positive gravity anomaly, but there was a pull down of the surface if it's in a fluid, and your measurements are closer to this pull down and lack of material at the surface, and so it's larger. So a heavy mass makes a net negative gravity because there's a depression that gets pulled down. And similarly, rising, a light mass has a positive gravity anomaly. And I found lots of data for this. In particular, this paper from Lamont, where this is the 32 submarine gravity measurements. The submarine can get below the surface and not be affected by the wave, and you can just have a sort of a land gravimeter, and you just sort of hover there for 30 minutes, and you can get a measure of the gravity. And it also is the largest, one of the largest gravity anomalies in the world. And so I applied my idea of, well, there must be something sinking just north of Puerto Rico. And I took the anomaly and said, well, the islands are always symmetric, the same both sides. So I just flipped what's on the Caribbean side and said, well, the island alone would be that. This is what you measure. And so the trench effect is this, and that could be fit with my different models. So this was the paper I published. I could redo the shape of this, of what the moho was, because you had a large, heavy mass down here, and that meant that the crust must actually go much deeper. Well, this didn't sit well with people at Lamont. I mean, I had taken their data but didn't like their model. And Xavier, I'm pretty sure, is the one who wrote this. I'll find out right now, because it just isn't his style of writing. And they pointed out it was either 43 or 47 mistakes that I'd made, and I forget which. And I made a reply, and I did not answer theirs. I just said, this is a difference between a mobilist point of view and a fixed kind of approach. And I followed up on this for my talk at the coming AGU. You had to have your abstracts in by December. I wrote an abstract. As you can see, I'm scheduled last in the morning, right before lunch. And Xavier said the room was packed, but he was in near a front row because he, you know, we were. He wanted to see if I made 43 more mistakes, I believe. And he says the room was full, but in the front row, he didn't see that a lot of people left. This was lunchtime. It was already running about 20 minutes late. But in January that year, this paper by Menard came out, and in his book, he had said that these great fracture zones in the Pacific were all great circles. And this was a correction to that. He saw they weren't. And it's because he had made a mnemonic projection, the great circle projection, where any great circle is a straight line. And these are not all straight lines, as they would be if they were great circles. And I saw this figure and said, gee, the ones up, you know, the Clipperton and such, but up here they seem to be curving this way, and down here they seem to be curving the other way. And this reminded me of the figure I had in my navigation textbook of a mnemonic projection, and you can see the equator is straight, and of course all of the meridians are straight lines because they're all great circles, but they curve up and they curve down. And I just said, well, this is a cleaner figure of that. What wasn't a Xerox, because they didn't have Xerox machine then. In our building, you could walk to another building, and there was one on campus. I tried to fit this with the ideas of computing something about a common pole. And there was a pole that was in Siberia. This is the one I worked on first. And I could take that, and if I decided that this was, you know, where the zero would be, and this would be like 45 degrees closer to that pole, you could calculate what the curves were, and I could calculate that they were better fit by small circles about these different fracture zones. And this is a cleaner version of the same thing. You can see that my dotted line calculations sort of fit it. Now, a pole in Siberia for the Pacific means nothing now, but the idea of opening with the rotation is one of the key theorems in physics and dynamics. It's why you treat the acceleration of the center of mass, and then you talk about the torques about the center of mass to get the angular accelerations, and it's the basis of most of mechanics. And I dropped the paper that I had essentially completed, and I still have the drawings that I never made slides from for the talk I was going to give, and gave the talk that you could fit in the Atlantic the fracture zones. They were small circles. They were magnetic anomaly rates that Fred Vine, who was my office mate part of this time, and I did some of these, and he did some of these, and we could. The other thing about rotation is the fastest spreading would be at the sort of equator from that Euler pole, and it would get less as you got further north or further south. And so pardon. This is the talk I gave in March, and I had prepared sort of a handout. And in fact, I was working on the handout the night before I took the train down to Washington. I mean, until 2 in the morning, I believe, and just brought some paper copies. And luckily, Xavier got one of them. So this was the paper. It's that the transform faults are extended to spheres, and there was an attempt to define plates according to ridges and trenches that were these were defined by. What this had was a mathematical rigor, and that meant that you could test it. You could make predictions, and you could test it against data, and that's the key to science, is that you can prove something doesn't work, and you can prove that it works pretty close, and that was my paper. I worked on this at Woods Hole, finished it at Woods Hole that summer, and mailed it off the last day I was there. So the Princeton doesn't like this at all, but I have Woods Hole is the address for this. The paper used some of the data by Lynn Sykes of earthquakes that they would fit also. They sort of agree with the pole that you would get from the fracture zones coming back. Not as well, but they don't disagree. I used that on the fault along the west coast, the San Andreas spectrum, starting in Baja California up, and you could get a pole. Well, the faults is pretty tight. The earthquakes is not quite so good. Right after I left Woods Hole, I came back a week later. Xavier was there, and that's when I learned what he was working on, and Walter Pittman. And Walter gave me the spreading rates in the southernmost Pacific, and I had a base map from Lynn Sykes that I made the same kind of thing that I had done in the Atlantic, and that there's a sort of pole, and you can get where it is in this direction from these lines. You can get how far it is from this by the spreading rate. And then this is the key part of the paper. It really looked like the plates were rigid, as Elsasser was talking about, that there's no deformation, ocean crust to continent. It's sort of a solid unit. And then these are the early papers on this, and I want to point out this much earlier paper by George Bacchus that has everything that I said in it. And I'll show you that paper. It was sort of a page and a half in Nature. There's no data. There's no. He says it if you read in the right place, and the fastest rate would be 90 degrees from the opening, and everything that's in plate tectonics is in this paper. George gave me this when I visited Scripps in '69. He was sort of sheepish and said, "You probably haven't read this." And I agreed that I had not. He said nobody did. And he said he was working on this. At the same time, he got started on the inverse theory with Freeman Gilbert. He said he wrote an NSF proposal to hire somebody to digitize. He was at Cambridge at the time, and had seen Vine's idea of the spreading. He wanted to hire someone to digitize the Project Magic magnet flights across the Atlantic, and he would do a spectral analysis of this and show that you got longer wavelengths, 90 degrees, right where he thought this pole might be, and that the frequencies, he didn't know you could match anomaly for anomaly. That hadn't been discovered yet. But the NSF turned it down, and he worked with Freeman on the inverse theory instead. Okay. Well, this is something that I hope that Richard Gordon will talk about, and I want to just get to a couple of points on this. And this is a VLBI measurement, radio telescopes looking at pulsars from a town just north of where I live and near Boston, Massachusetts, to a town that's not too far from Munich, Germany. And this is about 10 years worth of data of the distance between these two places. And there's data. Every 5 days, these we'll look at stars for 5 or 10 minutes each and switch around the sky. And the red line is not a fit to the data. The red line is the Nouvelle 1 magnetic anomaly prediction of how fast these should be separating. And you can see there's a remarkable agreement with the actual measurement. And similarly, this is Miami, Florida to Boston, Massachusetts. There's 0 and 0.1 millimeter error bar, no change at all. This is the same rigid plate. In the Pacific, the Aleutian Trench is closing, and Alaska is getting closer to the station that's in Hawaii. And another one of the measurements that came in at the same time is this, the measurements by Doris, and they have a computing their measured motion of compared to what the magnetic anomalies and rigid plates predict, and the data agrees with the magnetic anomalies and plates for stations all over the world. Doris had great coverage. Now, this is a remarkable paper that said, gee, Turkey seems to be getting pushed out of the way by Arabia coming up against the South Anatolian Fault. Xavier made measurements in that and showed that it agrees very well. This is a more modern with a lot of GPS stations. And you had another prediction of India colliding and it just pushing a wedge of material out to the side. And you can see with GPS, it really, they agree. This is the present, or last year's, where GPS stations are operating in the U.S. continuously. And they're mostly in the east because they've moved from the west to the east and just left a few behind. But these are the velocities. Now, you can fit most of the southern part with one rotation and subtract that away and look at the residual. And this is an earlier version of that. But you can see there's very little horizontal motion over what's called sort of stable North America. But as you get near the rebound from the glacier, you do get measurements. So you're really, with GPS, getting into stable North America. You don't even, they're just little tiny dots for the arrows. And as you get into the Basin and Range, it goes faster and faster, and very interesting patterns. And what I want to conclude with is that what last is Hess is right. It's mostly rigid oceans and continents. And the assumption of perfectly rigid plates is really no longer needed because you can measure it. When you only had measurements at ridges and velocities and nowhere else, you needed predictions. So I think the heyday of plate tectonics is gone because you got measurements instead of theory. Questions?